AP Calculus. First section 1-4 is on continuity and one-sided limits. There are 4 learning targets for this section. First, I can determine continuity at a point, and continuity on an open interval. And remember from the past, open interval notation is just like parentheses. So if I write like 4, 6, that does not mean to plot the point 4, 6. That means when you're looking at it from a perspective of a x-axis, you're allowed to go to 4 through 6. So you're allowed to look at open interval between these two. Number 2, learning target, is I can determine one-sided limits and continuity on a closed interval. Again, notation from the past, if it's closed, you'll know because they use brackets. So if I use the same 2 numbers, closed interval 4 to 6 means you can include 4, you can include 6, and all the numbers between. Open means start at 4, go to 6, but don't include those. Third learning target is I can use properties of continuity. And 4, I can understand and use what's called the intermediate value theorem. And sometimes I've seen it where they just use an abbreviation. You're allowed to do this on an AP exam as well. You can just call it IVT, intermediate value theorem. So we're going to look at highlights here. Continuity, like what it means to be continuous at a point and continuous at an open interval, as well as a closed one. We're going to look at the keyword one-sided limit and how that's different from the limits you've already learned. We're going to look at some properties and then intermediate value theorem. Okay, first part is on continuity in a continuous function, and this is from pre-cal. A continuous function is basically a function whose graph can be drawn without lifting your pencil. Like there'll be no interruptions in the graph, no holes, no asymptotes, no jumps. It's a nice smooth curve or graph. Now that was the pre-cal definition. Here's the calculus definition. It's a lot more detailed. The definition of continuous or continuity means a function is continuous at some point or some value c when the following occurs. And all 3 of these things must be true for a function to be continuous. Number 1, f of c is defined. That means whatever value they give you, when you put it into your function or you're looking at it graphically, the f of c has to have an answer. There has to be a point that has a y value. Number 2, second thing that has to happen is the limit of f of x as x approaches c exists. So the limit of f of x as x approaches c exists. And number 3, when number 1 and number 2 are met and they both have the same answer, then it's going to be true. So f of c is defined, the limit of f of x as x approaches c exists, and the limit of f of x as x approaches c is equal to f of c when the answers are the same. That is by definition how you truly know that a function is continuous. And again, that's the calculus definition, and this is extremely important that you know all 3 pieces. When a function is continuous on the entire number line, like from negative infinity to positive infinity, it's called everywhere continuous. When you can look at a graph or just an equation for that matter, and you know without a doubt that every single location on that graph is a valid point, there's no hole, there's no asymptote, there's no jump or gap, it's continuous everywhere continuous. If a function is not continuous, then it can be called removable or non-removable. So if a function is discontinuous, there's actually 2 types. And we did not learn this in pre-cal, so we're just going to look at these right now. They're fairly straightforward, but you need to make sure you understand the difference. So the two categories for discontinuity: number one, it's removable if the function can be made continuous by redefining f of c or a small hole. If there's a small hole in the graph, it's removable. Number two, non-removable. That means the function is or has asymptotes or jumps. Removable has holes. Non-removable has an asymptote or a jump. That's the key. Okay, looking at the screen now, you see the directions says to use the three conditions to determine if the following functions are continuous. So we're going to start with picture number one, and you notice that on your screen it is a parabola, and it does appear to have an open circle here indicating there is a hole. I know when you're looking at it graphically, you should be able very quickly to know the answer here, but you also have to be able to go through the steps. Okay, so even if we know the answer, this is what we're going to do. Step one, I have to tell you what the C is. So why don't we call C here, try to indicate where that is. I'm going to use 1 for that. C is 1. Okay, so what we have to do, looking back at our notes, is we have to see, is f of c defined? Is there an answer for it? And so we're going to say f of, and c is my x value. So I'm just going to say, what is f of 1? Now when I write it that way, I'm actually asking you more of a pre-cal question. I'm asking you, what's the y value when x is 1? So when you go to my graph, x1, and I go up to run into the picture, there's a big hole there. And so I don't have a clue what that answer is. Okay, it doesn't exist. There's not an answer. So undefined. And I actually messed up when I said does not exist. You only use those words when it's a limit. This is not limit. So sorry about that. Try to correct my mistake there. F of 1 is undefined, meaning there's not an answer. Okay, condition 2. Second step or condition in trying to figure out if a function is continuous is to look back at your notes to see if the limit of f of x as x approaches c actually exists. So does the limit of f of c as c approaches 1, is there an answer to that? Please notice my notation, limit f of c as c approaches 1. So if I put 1 in here and I look at it from the perspective of the graph, if I'm approaching, look at the x's, and as the x's get closer and closer and closer to 1 on the x-axis from both sides, the graph is doing what? Well, it's approaching a height. Now I know there's a hole there, and so when I ask you f of 1, you're trying to give me the y value for that, and since there isn't one, that's why it's undefined. But when we're looking at it using a limit is saying what are the y values approaching as c is approaching 1, then your value, your y's are actually, they're decreasing, and then they're increasing, but they're reaching, it looks like 3 on my picture. Okay, so even though the graph has a hole, there still can be a limit. We learned that in the last section. And then condition 3, based on my notes, you have to tell me, is f of 1, or is f of c, in my case 1, the same answer as the limit of f of c when c approaches 1. And we can tell when condition 1 and condition 2 are different answers, and obviously these are, then it is not true. And so because we've gone through the 3 conditions, that's the reason we can say this is not continuous. Okay? And then a lot of times they'll ask you, once you go through the three conditions, well, what type of discontinuity is it? And again, looking back at your notes, there's two types. Removable is when you can like redefine the f of c, or there's a small hole in the graph. Non-removable is when there's an asymptote or a jump. And so in this picture, it would definitely be removable discontinuity. So just be aware of that and be able to specify which type. Okay? Alright, so it's the same three conditions each time when we're talking about continuity. Let's take a look at number 2. Example 2 is g of x is equal to piecewise function of x squared minus 5 if x is greater than 0, and then g of x is equal to x minus 5 when x is less than or equal to 0. So remember from the past, to recall from about piecewise, when you're looking at it based on, let's start with this one, with the x squared minus 5, your job is to, just based on your past knowledge, know that that's a quadratic, that's a parabola, and the minus 5 is actually, this 5 is being subtracted from the entire problem, so that's a vertical shift. It's going to be pulled down 5 units. So you're going to start right here on the x-axis, and then I would throw in like a couple numbers. You can do that in your head. When x is 1, this is 1 squared minus 5, which is negative 4, so 1 negative 4 is on the graph. When I use a negative 1, likewise, negative 1 squared, still 1. 1 minus 5 is still negative 4. I'll do another one. When I use a 2, 2 squared is 4, and 4 minus 5 is negative 1. So 2 negative 1 should be on the graph, as well as negative 2, negative 1. Remember, it's a parabola, so we know it's symmetric. So the graph is this. Kind of just picture that in your head. It's a parabola shifted down 5 units on the y-axis. But piecewise is telling me this is the only piece I can show when x is greater than 0. And so go to your x-axis, and when I'm finding 0, I'm going to run down till I get to the graph. And anything bigger than 0, that means this graph needs to stay. Okay, so that's how we do a piecewise picture. Alright, so we're going to do this. We're going to erase, erase, and erase this little piece. And I'm going to try my best to show, I don't know how well, but this is supposed to be a big hole in the picture right there. Alright, next we are going to go, let's go with blue. We're going to graph y g of x is equal to x minus 5. And so based on algebra 1, we know to go to negative 5 and go up 1, right 1, up 1, right 1, so forth. It's just a diagonal line. Okay, but it's piecewise, and so we're only allowed to leave it when x is less than or equal to 0. So we're going to go to 0 on the x-axis. We're going to run down until we hit the graph. Oh, and this time it says equal, so I'm allowed to leave that blue point right there. Anything less than 0 is towards the left, and so I need to kind of just sketch, kind of connect these, straight line. Straight ray, actually, using a geometry term. And now I need to erase all the other points that are not part of that picture. Okay, so that one, there we go. Alright, so this is what we have. We have a straight ray here, and then it hits the y-axis at negative 5, and then it curves, more like a parabola. So this is the shape we're dealing with. We're going to start looking at continuity. The calculus definition has to meet 3 conditions. In your homework, I'd like you to do that as well. So condition 1, and we're going to go with 0. We're going to let c be 0 in this problem. And the book will tell you what c is equal to. Okay, so you don't have to worry about that. I think most of the time they will. Now, if they don't, it's likely just going to be the number that you see, like in this problem, that you see in the piecewise question. And over here, the reason I chose 1 is because that's where the hole was. Okay. Alright, so we're looking at f of 0 right now, and we're not doing a limit, okay? All we're trying to do is decide, is there an answer? Is there a y value when x is 0? When I look at the graph, x is 0, y value, yes, there is a value. It's at negative 5, because 0 comma negative 5 is a point on the graph. Okay, second condition. Then I have to look for the limit. Well, the limit of g of x, I used the wrong letter, sorry. Limit of g of x as x approaches 0. Okay, or I could use C here, either one. But the whole idea behind this is when I look at the x's and I approach them from the left and approach them from the right, what are the y's doing? Well, from the left, every time I choose like -9, the y's going to be down here. -8, -5, so forth. The y's are tending to go uphill. They're increasing. So when I get closer to 0, the y, the height of the curve, is actually at -5. Likewise, if I come in from the left side and like look at it this direction, the closer I get to 0, the y values are moving down the parabola and they're going to end up there. And so the height of the curve is going to be at -5. Again, this is a location on the graph. This is a limit, meaning the height of the curve. And then number 3, condition 3, since condition 1 is -5 and condition 2 is -5, since f of 0, or f, let me change that, since g of x, or g of 0 is equal to the limit of g of x as x approaches 0, since those are the same answer, check. We are allowed to say this graph is continuous. And it's continuous at that location. So I want to make sure and I make this clear. It's continuous. Ooh, sorry about that. It's continuous at 0 for sure. Okay. Now there will be some pictures for future reference. There will be some examples where overall, like this one, overall it is discontinuous, but they may even give you this diagram and say, all right, we want you to look at this piece, all the part I've highlighted in green, and ask you about continuity on this piece. You would have to say yes on that. As long as the condition 1 and condition 2 are equal, you have to say yes. But overall, it's discontinuous. So just the whole point in my comment there is pay attention to the C value, because when they change the value or they give you like a different section to look at on the graph, your answers may change. I don't want you to have the misconception that you're always looking at the entire graph. Now sometimes you are, but sometimes you're not. You're just looking at like a part of it or a section of it to make the call about continuity. So again, just be careful. And then we'll take a look at number 3. In example 3, I see f of x is equal to x minus 1, and it's divided by x squared minus 1. And when I'm looking at that problem, I notice right off, and hopefully you do as well, that the denominator is a DOS. It's a difference of squares. Anytime I see that, I want to simplify. So I want to call x squared minus 1 x plus 1 and x minus 1. I want to multiply those together. I want to factor it out, basically. Difference of squares. And the reason I want to do that is so that way when we look at the numerator compared to the denominator, we notice that there is a factor on top, x minus 1, that will divide out, cancel basically, to be a 1. And so now the problem, just because I've used a factoring skill, now the problem looks different. It's more simplified. F of x is equal to 1 over x plus 1. And so up front, I probably should have started with this. This original problem was a rational question. We've had that in pre-cal. We had that recently. It's a rational problem. Rational, they do different things. We know that from the past. So since I chose to simplify this, and that's always the best thing to do first, this canceled. Well, that means there's a hole at that location. And so when you're doing the criteria, again, we've done this in the past, you want to look for the vertical asymptote, and that's going to occur when the denominator is set equal to 0. So like x equals -1, You want to look at look for a hole, and if anything cancels, you want to do that. You want to set whatever cancels that has an x in it, and I had a factor up here that did so. Then I want to take that factor, x minus 1, and set it equal to 0, and solve that. And so this one would be x equals 1. So there's a hole at x equals 1, but there's a vertical asymptote at x equals negative 1. And then you also want to check out the HA, the horizontal asymptote. Remember, the fast way to do that is to compare the powers x on top and bottom. And so I see that, like in the original problem, or even this one, the x on top, there isn't one, so that would be x to the 0 compared to x to the first. The power on top is smaller than the bottom, and so when that happens, there is going to be a horizontal asymptote on top of the x-axis. So y equals 0, and make sure that you always write it with a y equal. Okay, so vertical asymptotes are vertical actually up and down, so x equals number, it's an equation, don't just give me negative 1. And remember, horizontal asymptotes are lines that run left to right, and the equations of those are always y equals. I don't want you to get that mixed up, because I've had people in the past do that. Okay, so if I have an HA at y0, then I'm just going to draw like this line. Okay, right on top of it. And then I'm supposed to have a vertical asymptote at negative 1. Alright, well, if I do that, it's going to be here. And then you can use your graphing calculator, of course, to speed it up. You can go back and do a table value. I'm going to kind of do this in my head with you out loud. So if I'm looking at, this is my equation. Okay, this is my simplified version. That's easier to do in my head. Then I'm going to, back to pre-cal, when we find a vertical asymptote, we choose a couple numbers to the left of the asymptote and a couple numbers to the right. Well, if my vertical asymptote's at negative 1, then I want to choose negative 2. Well, if I put negative 2 here, that's 1 divided by negative 2 plus 1. That's 1 over negative 1. Okay, well, 1 over negative 1 is negative 1. So at negative 2, the point goes right there. Okay, let's try negative 3. If I put a negative 3 here, that's going to be 1 divided by negative 3 plus 1. Well, that's 1 divided by negative 2. That's negative 1/2. So I go to negative 3 and down 1/2. And then I just kind of sketch it in, getting close to my asymptotes, and that's what it looks like in that section or quadrant of the picture. And then I want to choose a number to the right of negative 1, so I'm going to pick 0, easy to work with. 1 divided by 1 is 1, so at 0, 1, there is a point on the graph. Then I'm going to choose 1. If I put 1 in for x, that's just going to be 2 on the bottom, so 1/2. So 1 gives me 1/2. And so now I can kind of sketch this in that way, okay? And then the last thing I want to make sure I don't forget, there is a hole at 1. And so now you've got to go to your graph, find 1, and right there where that yellow mark is, that's supposed to be a hole in the picture. Okay, so after you get it all graphed, then you're back to doing the same thing we did in example 1 and 2. You have to make the call on condition 1, condition 2, and condition 3. Alright, so I'm not going to work all this out, but I do want to talk to you about my last comment I made about what part of the graph you're looking at. So let's say we're looking at a negative 2. If I use C as negative 2, then I'm asking you to tell me first, is f of negative 2, does it exist? Well, when I go to negative 2 and look at the graph, yes, I can find a location. Looks like negative 1. And so that condition 1 would be met. Condition 2 is, well, what happens when the limit of f of x or f of c, what's the answer to that when c approaches negative 2? Well, a limit is me looking at it x first, and as I get closer and closer to negative 2, what are the y's doing? Well, they're approaching the same thing. And so because of that, when condition 1 and 2 are met, then it is continuous at negative 2. Okay, this graph is continuous at that location. But the whole ballgame changes when I change the C value. So, what about 1? Well, does f of 1 exist? F of 1? No, there's a hole there. So condition 1, you'd write undefined. Condition 2, well, what's the limit as x approaches 1? What's this graph doing? Well, the graph is getting closer and closer to 1/2, we said. Okay, so that one, too, has an answer. Condition 1 is undefined. Condition 2, limit is 1/2. But because the first two conditions are not equal, and again, I just keep repeating that because it's super important, then that's why this graph is discontinuous at 1. So that would be a removable. This would be removable continuity, and then at negative 1, it would be non-removable. So I gave you 3 complete examples and hopefully reiterated the conditions over and over so that you understand what you're expected to do in these types of scenarios. All right, we're going to look at one-sided limits and continuity on closed intervals. So when this is new to us, one-sided limits, basically, when we're looking, I've been saying it, but I've just not been writing it down on purpose because I knew it was coming, but the limit from the right side, when we want, when the textbook is asking us about a limit on the right side, then they're going to write it this way. They're going to put the X, and then they're going to use the little arrow that means approaches, okay? And they're going to give you a number, okay? I'm just going to use C. But if it's the right side, they're going to use a little plus sign, almost like in a power position, and you'll notice that on your practice set. So like X approaches to positive. That just means come in from the right side. So when you're looking at it, let's say we're approaching 0, you're looking at it from right to left. Okay. When the limit is, or they want you to do a limit from the left side, they're going to use this notation, limit of f of x as x approaches c negative or minus. That's when they want you to look at it from the left side, that direction. Okay. One-sided limits are useful for certain types of pictures, like radical functions. It's very important you use that, like one-sided limits to figure out the answer. Step functions also are good practice problems with this idea because sometimes they're different answers, and you have to be careful and make sure you're looking at the right piece of the graph. But the green part's super important. If the limit from the right side does not equal the limit from the left, then the two-sided limit does not exist. So in other words, if I give you a picture and on the right side you're getting like, I don't know, 3 as an answer, and then when you look at it from the left side, the y values are approaching 2, when those answers are different, then overall the limit does not exist. And so just to make sure that you understand, we have been dealing with problems like this, and I just say x is approaching, and I just give you a number, or the textbook would give you a number. When you see a plain number with no sign here, that is a two-sided limit. That's a two-sided limit. Okay? But when you see the plus sign, that's a one-sided limit. They only want you to look from this direction to from the right, like coming in this direction. When it's a negative sign, they'll want you to come in from the left side and look at it that direction. But if you get 2 different answers, then this does not exist. And remember from the past, the notation you're going to use for a limit that doesn't have an answer is DNE. Only use that when you can't give me an answer. Okay, so we're going to practice these 3, and then we'll have to call it quits and kind of do the second part of the notes in the next class. Determine the one-sided and two-sided limits for each of the following. So if you'll pay attention to my example number 1, you notice I've given you a square root function as a graph. I'm going to call this g of x. Okay, so this is your graph g of x. The question is, find the limit of g of x as x approaches 0 from the right side. That's a positive. So my eyes are coming in. I'm approaching 0. Okay, my eyes are starting here, and we're moving this direction. When I'm doing a limit, again, I'm trying to see the height of the curve. So if I'm out here, the y's are up here. And then they slowly, slowly, slowly decrease. And so when I'm coming in from the right side, the graph, the height of this graph is actually going to the origin. Do you see? Going towards the origin. So this answer is 0. All right, now let's look at it from a different perspective. Let's do the next one-sided limit, and it now says, find the limit of g of x of this picture if x approaches 0 from the left side. So we're coming in on the left side. Of course, we're looking this direction, and we notice, like, I don't see any part of the square root function in here. There's nothing here. It's like I'm looking from the left, but there's no point on this graph. And so the closer and closer I get to 0, this graph doesn't exist here, so how can I find the height of it? Again, when I'm coming in from the left, this graph is only in quadrant 1. I can't find the height here or here. So this one does not exist. It's a limit, so we're allowed to answer it that way. And so now, third question. What's the limit of g of x as x approaches 0? So the right side gave me 0. The left-sided limit gave me does not exist. And so because the one-sided limits are different answers, then this one doesn't exist. The whole limit. I can't find an answer. Okay, let's look at example 2. Example 2 is the step function from Algebra 2. Remember to look for notation on your practice sets that have brackets around it. When you have brackets, that's the step function or greatest integer function. Notice that, and I've tried to make this clear, but I have I didn't do a great job, but all of these right here in yellow are supposed to be open circles, okay? So everything in yellow is open. So your graph is at closed circle, line segment, open circle, closed circle, line segment, open circle. And it just kind of like steps, continues to rise. This is called the parent function of the step function. Let's take a look at the limit. The limit of f of x as x approaches 1 from the right side. So we're going to come in this direction, okay? We're keeping our eyes moving towards 1. And when I do so, I can see this graph is actually like falling from the right side when I'm looking at it at that angle. And when I get to 1, I notice, oh, there's a hole there. So my eyes actually have to go to this level. So the limit of f of x as x approaches 1 from the right side, look at it again. Ooh, the graph goes to 1. So that answer is 1. That's the height. Now let's look at the limit of f of x as x approaches 1 from the left side. So this time I want you to visualize you're coming in this direction, okay? And when you do, you're trying to get to 1, okay? And when you get there, when I get there from the left side, all these points here are still points in that line segment, but that is approaching, that's still on the x-axis. So that answer is 0. All right, let me do that again. From the right side, all the values, remember the yellow is are holes, and the red is actually points. So when you come in from the right side and you're approaching 1, then like you're looking at this level, because this is still approaching, this is getting closer to 1 on the x-axis, but the y value is 1. So that's why the limit is 1. But on the other problem, when you're approaching it from the left side, you're looking at it, you're getting closer and closer and closer to 1. But at 0, it's 0. And at 0.1, it's 0. And at 0.9, it's still 0. And so that's why this answer is different. And so in a step function, often that happens. You're just going to have to be super careful, okay? And it does take some getting used to and some practice. That's why we're going to practice a bunch. But the limit, the two-sided limit, does not exist because these answers are different. And so for today's notes, and I know it's a long video, but AP Cal is going to be like that. It's just kind of the nature of the beast. We did look at Learning Target 1 to a point. We looked at it like here. We didn't even get to the open interval, closed interval stuff, so we'll have to do that next time. We did do part of Learning Target 2, part of it. We looked at the one-sided limits. And so basically we've done only pieces of Learning Target 1 and 2. We still have to look at open interval, closed interval, properties, and IVT. And so the textbook, you know this, is set up, it's college material, so every section has a ton of stuff in it. It will take us another day to go through the notes. Alright, so I hope that has helped and you're going to follow those, and I would like re-watch the video because I know I talked very quickly today, but re-watch it, make sure you understand what I have gone over so far, and then apply that to your homework sets.